Hello Bobcats. Today in this video we're going to discuss uncertainty of measurement or data. Now all measurements have uncertainty. What do I mean by that? Well, we know that a measurement can land or occur in between marked increments on an instrument. And you have to make a guess at that point or estimate. So let me finish writing this down and let's draw an example of that. So in this case, let's say I want to make a measurement. I have a ruler, so my instrument or tool would be a basic ruler. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 5, 6, 7, 8, 9, 10. And if I have it marked as centimeters, so this is 0 centimeters, 1 centimeter, and 2 centimeters, the marks in between would be 1/10 of a centimeter. Now, what if I were interested in measuring, let's just make an object up. So we've got this bar here, so let's draw this bar. Not a very good bar, but you get the idea. We have this bar. And if I notice where the measurement ends, we can see that the measurement lands in between my smallest marked increments on this instrument. And so when we look at this, we would say that it's 1.12. Those are for sure marked increments, and then we'd have to make this estimate. So that's 1.12, and let's guess that at 0.6. So here we would have 1.26 centimeters as my measurement. Now, so it's marked off in tenths, but my estimated digit is this last digit here, the estimated digit. And that's the smallest measurement that we can make on this tool or instrument. And so we could say that the precision of this is, or you can measure, the smallest measurement that can be made is to the 0.01 centimeters, which would be 1/100th of a centimeter, because my estimated digit was at the 100th of a centimeter, which is one place beyond the marked increment. Now, so how do we know we have good measurements or data? And so there are two terms we're going to discuss right now. The first one is precision. And what is precision? It is how close a set of measurements are to each other. And I will explain that or show you examples of that in just a minute. But we use standard deviation to determine precision. Now, standard deviation is a statistical problem, and we will not actually be determining standard deviations in this class, but you have to understand that that's how we determine precision. And then we have the other term is accuracy. That helps us know how good our measurement was. So let's look at accuracy. What is accuracy? Accuracy is how close measurements are to the true value. So how close measurements or a measurement is to the true value. And we use percent error to determine accuracy, and this you will learn how to do in this class. We will learn how to do percent error, and I will show you in a few minutes. So percent error determines accuracy. Now, when we are kind of giving you ideas of what this is like, or what is the concept of this, we use start with targets. So if I have 3 targets here, so there's a bullseye, in this target, and we have a target here, and then we have a target here. Okay, so now with those 3 targets, if I use a gun and hit these targets with a gun, or a bow and arrow and hit arrows with it, and let's say we happen to hit this target in these places, and let's put in 5 shots. So we took 5 shots for that target. These are very far apart. We don't, they're not close together, they're not grouped together, and they do not hit the target or true value, which is the bullseye. So these are not precise because they're not close together, and not accurate because they do not hit the accurate or true value, which is the target in this case. But let's say we shoot again and all of 5 of our shots hit right there. Well, now they're grouped close together, and because they're grouped close together, they would be precise but not accurate, and the reason they're not accurate is because they didn't land on the true value or the bullseye. And then if we have all of them land right at the bullseye, then they would be precise because they're all grouped close together and they are all on the true value, so they're precise and accurate. Now that's using targets to explain this, but we don't use targets in chemistry. We collect data from measurements. So let's look how this works when we look at data from measurements. So let's take another sample here, and let's look at some data. So I'm going to look at volume versus mass versus volume, or density of an object. So we have mass and volume on this, and then with this graph the same thing, mass and volume, and then on this graph the same thing. Now let's say that the true value, let's make the green, let's do this, the true value, if I took a mass and a volume, and the first mass and volume I took was here, and then I took another mass and volume and it's here, and then here, and then here. So we notice that the true value is this here. This is the true value. Now, what if I had students, 5 different students get the density, mass and volume of an object, and we have one student gets it there, another student determines it here, another student here, another student there, and one here. Well, these are, none of them are close together, and they are not along the true value. So this is not precise nor accurate. And we also have a term, we call this random error. Now, because it's random error, it's very difficult to determine and fix the problem. And it's random because they're all equally far from the true value and from each other, and we just don't know what's causing it. It could be a student didn't do a good job at measuring those measurements, making those measurements. It could be that the instrument is off. It could be the weather. It could be all kinds of things. Now let's say again we have, we got to do a true value, so we've got our true value is along this line here. That's true. But now I get the 5 students to make measurements, and they measure one student, they measure here, there, here, there. I need one more. Let's put it here. So, and if I do a line of best fit, we notice that these are grouped very close together along that line of best fit, but the problem is they do not match the true value. So these are precise but not accurate, and this kind of collection of data is called a systemic error. Systemic error. Now, a systemic error is easier to find and easier to correct because we know that there's a lot of precision. Usually what happens here is that the instrument or tool has been calibrated wrong, and all you have to do is calibrate it so that the values meet the true value. And the last one is if we have our true value. So the green marks are the true value, and then we have students that actually are able to get information that are very close to the true values, and so they are actually grouped close together, so they're precise and they're accurate, and there's no error here, so we don't have a name for that. So those are precise and accurate, and that's looking at data. Now the other thing is, earlier in the lecture you'll notice that I said that precision also considers how small the measurement can be. And so how does that relate to a grouping of data? Well, let's define precision of an instrument. So precision of an instrument is the estimated place value following the smallest marked increment. Okay, so let's say I start out and we make a measurement of mass of an object, and we get a measurement of 4.2, 4.3, 4.4, and so forth, and it's measured in grams. There is some precision to this because, and we look at it, most of the time, if the marked increment is the same, and your estimated digits are close together, then there's a good precision there. But we can make it even better by measuring something smaller. And all of a sudden we'll notice that, let's say 4.232, 4.3, 1, and then 4.33, and we made those measurements, and guess what? They're actually grouped closer together, because now the 10th of a gram is now the same, and we're off just by in the hundredths place. So we've actually grouped them closer together, and we can get even closer with a smaller measurement. So 4.321, whoops, 4.321 grams. Let's say 4.319 grams and 4.320 grams. Now I know that the hundredths place is not exactly the same, but they are very, very close together, and the thousandth are close together too. So we've even grouped them closer together than they were before. So the smaller the measurement, the closer, that's a CL, sorry, CL, closer, the grouping of data. Resulting in more precision. In measurements that are more precise. So that's how even the smaller the marks, you can also call that the precision of the instrument, because the smaller the measurement, the closer the data groupings are, the more precision there is. And the last thing I want to talk on this video is about accuracy. How do we determine accuracy? So, accuracy is determined with percent error. So, determining accuracy with percent error. And percent error is equal to the absolute value of the experimental value or experimental measurement minus what is true, the true value, divided by true value. And it's absolute value, because let's say this was smaller than the true value and you got a negative, but you can't have a negative percent, so it's the absolute value of experimental minus true divided by true times 100. And that gives you your percent error. And we will stop with that. If you want an example of percent error and doing percent error, you can look at the PowerPoint that I have given you. And that is uncertainty of measurement. The next thing we're going to talk about is how do we record measurement, and we use significant figures to do that. So the next video is about significant figures. Have a good day.